let's consider this example using the simulation here. I'm going to pull it up in front of us. Okay, so here's a river. What we see here in greenish is a river, and this is the ground, and we have a tiny person here. These arrows here are vectors for the different velocities that we can set up. For example, I'm going to take this one here and try to move it to 0. So the person has 0 velocity. And I'm going to do the same thing for the velocity of the water. So we have it as a still river. Oops, that's still not 0. Okay, I think we got 0 here. So when we tell it to start, we have a boat here that's moving relative to the water, but we have these indicators here that show us that the water is not moving. The ground is not moving either. When I position my mouse on top of the river, my frame of reference or reference frame is written here. For example, here it's river, here it is ground. Now, what I'm going to do is I'm going to reset it. Unfortunately, that's the only way to set up things. And then for this person here, I'm going to try to set up a different velocity. Okay, let's see if I can pull it out. So I'm going to try to set up a velocity where this person can cross the river. So to a certain degree, I'm trying to set up the horizontal velocity of the person as 0, and then the vertical, according to the screen, velocity to be, in this case, 90. So if we start, okay, we'll see our person here crossing the river. There is no issue. Now, moving at a constant velocity, if we would like to find how long it's going to take the person to travel, for example, if we know the width of the river, we can find it out. And notice the motion is the same, whether I'm using the frame of reference of the river or the frame of reference of the ground. I'm seeing the same thing. That's because the river is not moving relative to the ground. Okay, now let's reset this. In this case, our river is going to be moving at 10 units per second. And then again, I'm going to try to give him a velocity in this direction. It does not have to be that large. And I'm going to try to remove this one. Okay, got it. Now if we start, notice this first. Relative to the river, the person is moving in a straight line. However, relative to the ground, look at the way the person is moving relative to the ground. So actually, unfortunately, I cannot show you both, but you'll see there are two arrows for the velocities, the 10 and the 19.5. Okay, the good thing about the simulation, he will go back and we can see it again. Relative to the ground is straight motion, straight motion. Now here, you see both velocities. Essentially what happens is, the person also has the horizontal velocity that the water has. So the overall velocity of the person is the velocity of the water relative to ground, plus the velocity of the person relative to the water. The velocity of the person relative to the ground is the velocity of the person relative to the water, plus the velocity of the water relative to ground. The sum of these two velocities, you add them up. You see them, the two arrows that are going to appear there. Relative to water, of course, is just the velocity relative to the water, in this case 19.5. Now, of course, if our velocity is going to have also a component relative to the water, in the same direction as the direction of motion of the water, my overall velocity is going to be 15, 5 plus 10, along the direction of motion of the water, and then the other one. I have it in this case at 18.5. So the overall velocity is going to be, of course, the hypotenuse, and you get it by finding the square root of 15 squared plus 18.25 squared. Okay, let's reset it and try another case. Let's have this person move in the opposite direction. Okay, you notice? So now you subtract the 17.5 from the 10 that you get for the velocity of the water relative to the gun, because they are in opposite directions.